There's a request to see example 16.9 worked in class. We didn't quite work it, although we did discuss it on the quiz. I thought I'd post it here though. Alright, part A says, what is the electric field at point A due to these 2-point charges? So we've got one that's a positive 50 microcoulombs and one that's a negative 50 microcoulombs. Well, the first thing to do is to draw which direction these electric field vectors will point from each of them, and then the next step will be to add them up as vectors. So we look at the electric field from charge Q. It's a positive charge, so it points in the up direction, always away from a positive charge. The electric field from Q1 is toward Q1, and because it's negative, it's going to be, I should say, it's on the line between A and Q1. Because it's negative, it's toward Q1. So here is E1 at that point and E2 at that point. And E at A is equal to E1 at A plus E2 at A. Right, so let's first, we know the directions. Let's see. Tells us this is 26 centimeters, and this is 26 centimeters as well, and this is 30 centimeters above charge 2. Okay. So there's the triangle. We can find out what this angle is. What should we call it? I don't know. Let's just call it alpha. It's a little fish symbol. Some people call it a fish anyway. It's the Greek letter A. It's alpha. Okay, so, oh boy, let's just look at this. Oh, they made it easy for us. So this is 60 centimeters, and they basically tell us that alpha is 30 degrees. Anytime you have the hypotenuse twice as long as the one of the sides, then you have a 30, 60, 90 triangle. That's not hard to imagine why that would be. Here, let me just, because if you drew the other side of this, or I should say, if you kept drawing the triangle, then you'd have a 60, 60, 60 triangle. And so it's just half of one of those. That means this angle's 60, this angle's 30, and this is a 90-degree angle. All right. So let's find the length of E1 at A. It's, if you remember, the equation is just K times the charge, this is Q1 that we want, over the distance separating those 2 points squared. So K is 9 times 10 to the 9th. I'm not going to worry about units. I just know it's going to work out to be newtons per coulomb. That's the units of electric field. Okay, Q1 is minus 50 times 10 to the minus 6. And again, I'm not worrying about units. Oh, I put a minus sign there. It's a good mistake to make because remember, I already drew the direction. That told me which direction the electric field pointed. The negative sign told me that already, so I don't have to include it here again. In fact, it will confuse me if I do. Okay, and then R is 0.6 meters. So square that. All right, 9 times 5 is, well, let me do one more step. So we've got 9 times 5 on the top, and then we divide by a 6, and now let's just take care of the powers of 10. The 9 I didn't change, so 10 to the 9 here. This one I had to divide by 10 once. So this is 10 to the minus 5 now instead of 6. And then down here, 6 squared. Down here this was 6 times 10 to the minus 1. So 10 to the minus 2, because 10 to the minus 1 squared is 10 to minus 2. Okay, so we've got 45 on top and 36 on the bottom. And then 9 minus 5 is 4. And then I want to add 2 because I'm dividing by 10 to the negative 2. So 9 minus 5 is 4, add 2 times 10 to the 6. And remember, I said it would be newtons per coulomb. Alright, so this looks like this is 4 times 9, and this is 5 times 9. So it's 5 over 4. That's 1.25 times 10 to the 6 newtons per coulomb. Alright, and now we need to find E2 at A. Again, it's just K. Now my subscript is different because I'm dealing with the second charge over R squared, and R really should have a subscript on it. This would be R1, and now we're dealing with R2. Okay, again, 9 times 10 to the 9th. Q2 is again 5 times 10 to the minus 6. 50 times 10 to the minus 6. And now we've got 0.3 meters squared down here. Alright, so the only difference is instead of having a 6 squared down here, we've got a 3 squared now. So this is 45 over 9 times 10 to the 6th newtons per coulomb. And this is just 5 times 9, and this is 1 times 9. So that is 5 times 10 to the 6th. Alright, now we've basically reduced this problem to one of those vector problems that we saw in chapter 3 in the homework. And you just add those two vectors, you find the resultant. It looks like this. E2 has length 5 and E1 has length 1 1/4. So it'd be something like that. And the resultant vector will be there. This is EA, the electric field at A from these two charges. Okay. B is even easier, and this is like the one that we saw in class. So here, let me just get a different screen. Alright, so let's do part B. Because B asks what the electric field at point B is. So again, let's just first write down the directions, and then we can write down the magnitudes. So the direction of this one is away from the positive charge. This is E2 at B. And the direction for this one is toward the negative charge. So this is E1. Sorry. Just undo that. Okay. E1 at point B. Okay, and the resultant, we can already tell, is going to look something like this. This is EB. Alright, but let's just work through this a little bit. Okay, we can find out what the length of E2B is, it's K times Q2 over R2 squared. This is a different R2 than we used before, but I didn't want to add another subscript. This is now this distance. And in fact, R2 is the same as R1. You can see that Q2 is the same distance away from B as Q1 is away from B. And so that's going to make both of these vectors the same length because they both have the same magnitude for the charges. And that's how I know, just going into the problem, that EB is going to point directly to the right. If this were slightly less than 50 microcoulombs, this vector wouldn't be quite as long, and you'd end up with an EB that points above the x-axis. So that's what I was saying in class was if these distances weren't exactly the same, or the charges weren't exactly the same, then you wouldn't get something that points directly right. The quiz question basically said that it's a possible direction. None of the other directions were even possible. Okay, let's write this down. We've got 9 times 10 to the 9th. Oh boy. And now the distance is given 0.4 centimeters. Okay, so Q2 is 50 times 10 to the minus 6. And we have 0.4 meters. Oh, whoops. That's 0.4 meters. It gives it as 40 centimeters. Okay. 0.4 meters squared. All right, this looks like the other problems that we had, which we had 45. Now we've got 4 squared down here. And we've got 10 to the 9th, 10 to the minus 5th, all over 10 to the minus 2nd. All right, so you got 45 over 16. If you've forgotten, let me just show you. So it was just times 10 to the minus 6. That's what all that stuff in parentheses was equal to. So times 10 to the minus, or 10 to the positive 6. Okay, 10 to the 6th newtons per coulomb. Okay, this one's not quite as easy. This is almost 15. So we're going to call this 9 times 5, and this 3 times 5. So 9 divided by 3 is 3. It's not quite exact, but it's close. Times 10 to the 6th newtons per coulomb. The book actually has it, it's 2.8, but I say close enough. All right, and now we want to find, we're going to need to add E2b to E1b, which points in this direction. So E1b. And really what we want is the x component of this, and then we'll add it to the x component of E1b. Oh, by the way, E1b is just equal to E2b. They have different directions, but they have equal magnitudes like we were discussing. Okay, so really, if we can find this, which is the x component of E2b, let's call this theta, like they did in the book. If we can find out what this is, we just double it and we get the length of EB. Because you get one of them from E2b, you get another of the same length from E1b. Okay, so we know that the cosine of theta is equal to This is the adjacent, which is what we're looking for. This is, can I call it EX? Is that alright? Alright, EX over E2B. Alright, so EX is equal to E2B times the cosine of theta. Okay, how are we going to find theta here? Well, we know that the cosine of theta, okay, this is also theta right here. And we know that the cosine of this angle is the adjacent over the hypotenuse. So that's 26 centimeters over, this is cosine theta. It's the adjacent, 26 centimeters over the hypotenuse, which is 40 centimeters. Okay, so centimeters can cancel. What do we got? 13 over 20. And that's about equal to 2 times 7 over 3 times 7. So it's about 2/3. So E2B we know is 3 times 10 to the 6 newtons per coulomb. Now we need to just multiply that by the cosine of theta, which we found was 2/3. 3's cancel, and you get 2 times 10 to the 6 newtons per coulomb. That's EX. The length of EB is equal to 2 times that, because you'll have this other EX that contributes to the length of EB. So EB is right here. It's all of that. Alright, so 2 times EX is just equal to 4 times 10 to the 6 newtons per coulomb. And that's the length. The direction is, as we drew it, directly to the right. Hopefully that makes sense.